We're going to get started. So this is the semi-annual Resnick lecture. We are now having Resnick lecture about twice a year. And we have this lecture in memory of Robert Resnick, who was a faculty here for a number of years, quite a number of years. And in fact, I was reading on his Wikipedia page that while he was here, he authored or co-authored 7 textbooks in physics. So that's pretty impressive. Of course, the most famous is the textbook that he wrote with Halliday, starting in 1960, and that book has been issued over and over in new editions, and I think they're on like the 10th edition now with Walker kind of running things. And so this has been a very influential book in physics education. And he was also an influential professor when he was here. Unfortunately, he passed away a couple years ago. We've had this lecture since the 1990s, and we've had quite a number of well-known speakers. We had Kip Thorne, we've had Leon Letterman, we've had Mandelbrot of fractal fame, we've had Roger Penrose, we've had many people, Carl Sagan, and we're very honored to have our speaker today. Today it's our honor to hear from Professor Sajeev John from the University of Toronto. And he's had a long and distinguished career, many more awards than I could possibly even read to you here. He got his bachelor's degree from MIT and his PhD from Harvard University, and then he worked as a postdoc at the National Sciences and Engineering Research Council of Canada, and also at the University of Pennsylvania, and was a worked as a laboratory consultant with Exxon. He was a professor at Princeton University in the late 80s, and while he was there, he co-invented with Eli Yablonovich something that's extremely cool, which is these photonic crystals. And I only know a little bit about them, but a lot of the things that you see in solid-state physics with block waves and things like this, you can actually do it with light, with these photonic crystals. So it's very, very remarkable research. He's the winner of the King Faisal International Prize in Science, which he shared with C.N. Yang, and he's the first ever winner of Canada's Platinum Medal for Science and Medicine. He is the winner of the IEEE LEOS International Quantum Electronics Award, which they gave for the invention and development of light-trapping crystals and the elucidation of their properties and applications. He's the IEEE Pioneer Award in Nanotechnology Award, the IEEE David Sarnoff Award, and he was selected as a Thomson Reuters Citation Laureate. Another impressive thing, and there's many more awards here. It just goes on and on. So we are just extremely honored to have you here and to hear from Professor John. And so let's please welcome him.
Thank you, Joel, for that very kind introduction. It's really an honor for me as well to be here and give a lecture named after such a renowned educator. And let me congratulate the fine work of our student here for winning the Resnick Prize. My talk today will focus on a particular application of photonic crystals, which may have very near-term implications in the field of solar energy harvesting. Photonic crystals are widely known for their light trapping capabilities. However, this wave interference-based light trapping has not been fully recognized in photovoltaics, especially in the case of silicon solar cells. Silicon being an indirect bandgap semiconductor, absorbs sunlight only very weakly at long wavelengths, and to compensate for this, they typically make the solar cells quite thick. This, however, leads to a large amount of bulk recombination losses, and as a result of that, the efficiency of silicon cells has not increased dramatically over the last couple of decades. And what I'd like to show you is the possibility that photonic crystals can make an impact in a twofold manner. One is to increase the efficiency of silicon solar cells beyond 30%, and at the same time to make them much thinner by maybe a factor of 20 than traditional solar cells. So just by way of introduction, as you know, the sun is the most abundant source of energy that we have. Approximately 173,000 terawatts of solar energy strikes the Earth continuously, and according to the US Department of Energy, this is more than 10,000 times the world's total energy use. On a more individual basis or local basis, the amount of power impinging in the upper atmosphere is about 1.37 kilowatts per square meter, and on the surface of the Earth at sea level on a clear day, it's approximately 1 kilowatt per square meter. So that's what we're trying to harness by some photovoltaic technology. A traditional silicon solar cell, as I've depicted here, absorbs photons from the sunlight. It creates an electron-hole pair, and there's a competition here between trying to absorb the most amount of sunlight, and typically for that you need a relatively thick piece of silicon, and the other process is for the electron and hole pair that are generated to diffuse or migrate to the contacts to provide power to an external load. And it's this balance between these two objectives that usually defines the architecture of a solar cell. So typically you have some doping, an N-dope and a P-type region, where carriers from, say, one of these N-type regions can diffuse into the other region, leaving behind a net positive charge, and the result is an electric field that occurs across this junction. When carriers diffuse around inside of this bulk silicon region, when they come to the junction, they are separated in charge, and as well, the minority carrier, in this case the hole, the positive charge, has a very difficult time re-entering this region so as to recombine and to dissipate the energy. So this is the strategy behind what goes into a solar cell. And typical silicon materials that we have right now, the module efficiency has been growing slowly over time. Right now, if you buy a silicon solar cell or a module, its efficiency is in the 17 to 20% range. In terms of laboratory solar cells, there are a number of world records that have been set that are much higher than those module efficiencies. And just last year, the efficiency of crystalline silicon went up to 26.7%. That was done by a company by the name of Kaneka in Japan. And the cell thickness there was 165 microns of silicon. If you have multi-crystalline silicon, the efficiency record is down to 22.3%. There are more defects in the structure and more places where the charge carriers can recombine. Additionally, there are a number of thin film structures, starting with this gallium arsenide structure, which has demonstrated an efficiency of about 29%. This is a direct band gap semiconductor, so it's much more straightforward to absorb the carriers, and the thickness of that was about 3 microns. Other thin film structures include copper indium gallium diselenide, 22.9%, cadmium telluride, which is also used in certain solar farms with about 10 micron thickness, with similar efficiency. And then as you go down, there's been a lot of excitement surrounding perovskite materials, which can be created from a solution-based starting point, so very inexpensive to produce. And finally, organic solar cells, which have much lower efficiency. But despite all these efficiency records, if you look at the actual market, about 95% of the market share is in silicon. So this is really where the action is. If there's a way of making these cells more efficient as well as thinner, so as to have some of the attributes of flexibility that you have for the thinner ones. That would be a very important achievement. Now, many years ago, two famous scientists, Shockley and Queisser, defined some of the limits to the efficiency of solar cells based on the nature of the semiconductor band gap associated with the material. So what I've plotted here on the vertical axis is where the energy that's being absorbed by the sun ends up as a function of the band gap of the semiconductor under consideration. So the red region, the pink region here, corresponds to a material with a relatively small band gap. So there are photons from the sun that have a much higher energy than the band gap energy. They create a high energy electron hole pair, but the electrons then scatter and relax to the band edge energy, and all that excess energy is given off in the form of heat. On the other hand, if you make the band gap larger, there's less of that thermalization loss, but this blue region depicts the range of energies where the sunlight falls below the band gap and it's not absorbed at all. So this is not being converted, it's just being reflected or transmitted without being used. And Shockley and Queisser considered the balance between these two effects and discovered that the optimum occurs somewhere around here, band gap energy between 1.1 and 1.4 electron volts, where both silicon and gallium arsenide lie, which would have the maximum possible efficiency. So here I show a chart for the maximum possible efficiency of a silicon-based solar cell with a band gap energy of 1.12 electron volts. There's about a third that goes away into thermalization. 19% falls below the band gap and cannot be absorbed. And then there's also some entropic effect due to finite temperature, which reduces the voltage of the solar cell. So about 14% is lost there. But they suggested that the maximum thermodynamic efficiency at room temperature for a silicon solar cell would be slightly under 33%. So this is the objective. Can we get as close as possible to this as possible? And this requires that 100% of the sunlight above the band gap should be absorbed. That's also something that is impossible to achieve. So typically solar cells have, silicon cells have much less efficiency, and as you can see here, the current world record is only at 26.7%. Here you see a little bit more detail about the solar spectrum as it's seen on the face of the Earth. This is the red curve as a function of wavelength. It covers a very broad spectrum. And on that same graph, I've plotted the absorption capability of silicon as expressed by the imaginary part of the dielectric constant. That's this black curve. So as you can see, the absorption is very good at short wavelengths, 500 nanometers and shorter. But as you go to longer wavelengths, you get less and less absorption, especially in this indirect band gap region, where if I replot this imaginary part as an effective absorption length, you start with an absorption length down here in the blue region of tens of nanometers, and over here you're on the scale of tens of centimeters, and no one's going to make a cell that thick. And so the ideal is to have some light trapping mechanism that will allow you to absorb as much of this spectrum as you can over the entire range of 300 to 1200 nanometers. And so the subject of solar cells has been around for quite some time, and the experts in this field have suggested various ways of trapping light, one of which is described in this simple argument where they consider the rays of sunlight as being literally rays without any wave character. And this is something that is called random statistical ray trapping, or Lambertian light trapping. And the idea was that instead of having a flat surface to the solar cell, maybe you make some randomly rough surface, and as sunlight impinges on the surface, it could be randomly deflected by some angle, bounce back off a mirror at the bottom, and when it comes back up to the surface, if the refractive index of this material is high enough and the angle is large enough, it'll get bounced back by the effect of total internal reflection. And so the question was, well, maybe one could design a structure so that you could have many, many bounces and extend the path length of sunlight at long wavelengths sufficiently so that quite a bit of it could be absorbed. And here's some more details of the argument. The Lambertian surface is one that is assumed to deflect rays coming in, say, at normal incidence by a distribution of angles given by the cosine of the angle relative to the normal. And as you know from simple first-year physics optics, that if the angle is greater than some critical angle defined by 1 over the refractive index, you'll get this phenomenon of total internal reflection. So let's suppose that we have a certain number of rays that are coming in and they bounce off at random angles, but defined by this distribution function. The probability that the light would escape is defined by it lying inside this cone. And if I weight this set of rays with respect to this distribution function and then integrate from 0 up to the critical angle, such that the sine of the angle is 1 over n, I find that the escape probability is given by 1 over the square of the refractive index on a single bounce. And then you can ask, what is the average path length due to one bounce? That again, it's 2L, the thickness of the cell divided by the cosine of angle theta, multiplied by this distribution function. And then the average path length of a single bounce is actually 4 times the physical thickness of the cell. And then we'd like to have many bounces, not just one. You could ask, what is the probability that it'll make an integer number m bounces before it finally escapes? And in order to do that, on the first m minus 1 attempts, it should not escape with probability 1 minus p. And on the final mth attempt, it does escape with the probability p. So this defines a distribution function for the number of bounces. And you can calculate the average number of bounces with respect to this distribution. And it turns out to be just 1 divided by p, or in this case, n squared. So by this statistical trapping argument, the average trapping length would be given by the average path length on a single bounce multiplied by this average number of bounces. It turns out to be 4 times the square of the refractive index times the actual thickness. So this has been a benchmark for defining what is a really good absorber and what is not. And so far, no real solar cell has actually managed to exceed this, what's called the Lambertian limit. In the case of silicon, the enlargement of the path length is by about a factor of 50, and that's what gives rise to these current efficiencies. And what I'd like to show is that using photonic crystals, one can actually surpass this long-standing Lambertian limit. So let me just give a brief introduction to photonic crystals. Unlike the previous picture of statistical ray trapping, photonic crystals make use of the wave nature of light and the wave interference effects that are associated with it. I started out in this subject thinking about whether it would be possible to create bound states of light in analogy to the bound states of electrons in Schrödinger's equation. And what I've done here is to write down the electromagnetic wave equation in a form that looks as close as possible to Schrödinger's equation, where the spatially varying part of the dielectric constant in this case is the analog of a potential in Schrödinger's equation, and the average part of the dielectric multiplied by the square of the frequency is like an energy eigenvalue. And if you're dealing with a real positive dielectric constant where epsilon 0 is greater than the maximum value of the fluctuating part, this would require that a bound state, if it were to exist, would occur within the positive energy spectrum above the highest of the highest potential barriers. So that's what makes this a difficult problem. But we were able to show that by arranging dielectric structures in the right way and creating a band gap in the spectrum of light, one could create these localized modes by then introducing some deviation from periodicity over and above the periodic structure. And this is a finite difference time domain simulation depicting a localized bound state of light around a defect in a photonic crystal. So the red and green arrows were the electric and magnetic fields, and the shading represents the energy density. As it turns out, we don't need to go to such an extreme type of light trapping in the solar cell case, but it does still rely on wave interference effects, actually at energies that are higher than where a band gap would actually occur. And here's a depiction of a photonic crystal that I was involved in making. It's a material made out of silicon, created by starting with a template consisting of opals, dielectric spheres made out of silicon dioxide, and then infiltrating this material with silicon and then etching away the original silicon dioxide template, leaving what is called an inverse opal structure. So this is an SEM picture showing the actual structure here. The diameter of these spheres is 850 nanometers. This has a complete band gap, an absence of electromagnetic modes over a band near the 1.5 micron wavelength. So this is a photonic band gap material. It wouldn't make a very good solar cell because it has a lot of surface associated with it, and carriers can recombine its surfaces, so we need to have something a little bit more appropriate to the application in mind for photovoltaics. Another feature of that photonic crystal that I just showed you is how it changes the electromagnetic density of states. If I just had a homogeneous medium, the electromagnetic density of states, the number of modes per unit frequency interval, would simply be a parabolic curve without any specific features associated with it. This photonic crystal has certain regions where the density of states is much lower than that, and in this part of the spectrum, this is the complete photonic band gap, no modes whatsoever. But in addition to that, there are regions where the electromagnetic mode density becomes much higher than would happen in a uniform or homogeneous medium. And in the case of photovoltaic light trapping, the action that I'll be focusing on is in these regions where there is a very high density of states, where you can get a different type of light trapping due to slow light modes, as they're referred, in which the light is bouncing around inside the structure and remaining there due to wave interference for absorption to take place, even though the absorption is intrinsically very small. So what I'd like to show is that wave interference-based light trapping in the higher bands of a photonic crystals offers a route to unprecedented solar absorption beyond the Lambertian limit, and as a result, higher power conversion efficiencies than have been demonstrated in real solar cells so far. And it's associated with the enhancement of the electromagnetic density of states, different types of refraction or coupling of light from normally incident sunlight into a thin film, where again the refraction can be what I refer to as nearly parallel to the interface into these slow light modes. And in fact, what we've shown is that in a film of silicon, considered a thin film of only 10 microns of thickness, it's actually possible to absorb 98% of the sunlight over this broad spectrum between 300 and 1100 nanometers. And this solar absorption beyond the Lambertian limit allows us to make silicon structures much, much thinner than would traditionally be possible. And those are thin as well as flexible, and it greatly reduces one of the major recombination loss mechanisms in silicon. That's what allows the efficiency to go up. In this case, our theoretical prediction suggests that it's possible within a realistic structure using experimental parameters for these recombination rates up to 31% compared to the current world record of 26.7 and the thermodynamic limit of 33%. And so some of these structures have already been fabricated either by wet etching or dry etching methods, and at least the optical part of the measurement seemed to agree with what we predict in terms of the amount of optical absorption that would be possible. Here's just another simple two-dimensional paradigm expressing some of the underlying physics behind how this light trapping is taking place. So consider some imaginary photonic crystal, say a square lattice of rods such as this. This is not a solar cell, of course, but sunlight impinging from many different directions at a range of frequencies. The amount of light that would actually be absorbed in this structure, if it's made out of silicon, depends on a number of different factors. The first is what I call the quality factor of various optical resonances that defines the dwell time of light in the structure, the density of such resonances, or the density of electromagnetic modes, which we want to be high, and then the coupling efficiency of light from the air into the structure rather than the light just being reflected back out. And so for this particular simple illustration, the electromagnetic mode structure is depicted over here. There's a small band gap in this two-dimensional photonic crystal, and then there are some higher bands which are relatively flat, as you can see here, compared to the linear dispersion down here. These are the slow light modes that I'm referring to. And so when sunlight impinges on this structure, the law of refraction is actually not as simple as something like Snell's law. It depends on the shape of the surfaces of constant frequency in the structure. And in this case, we can show that a light beam with an initial wave vector coming in like this would find the isofrequency surface associated with the incident frequency and then propagate in a direction that is normal to these surfaces. That's the direction of the group velocity. So it would actually be propagating nearly parallel to this interface. And because of these flat dispersion relation, what that means, it's bouncing back and forth many times in the vertical direction here. So that's part of the mechanism behind what I'll be describing to you. And now what I'd like to go to is some of the actual structures that we have in mind for realistic solar cells and how these photonic crystal concepts enter that. One of the metrics for defining how much light is actually absorbed is referred to as the maximum achievable photocurrent density. So what it is simply the solar spectrum that I showed you a picture of earlier as a function of wavelength over this broad range. It's called the AM 1.5 solar spectrum, multiplied by the absorption coefficient of the structure that we have in mind due to wave interference effects, divided by the photon energy and multiplied by the electronic charge, which converts the amount of light absorbed into an effective photocurrent density. And so this is one of the parameters that we'll be looking at in various different structures as I've depicted here. On the right-hand side is a photonic crystal architecture, which was actually developed in Professor Sean Lin's group, which consists of these square lattice array of sort of parabolic-looking pores. The lattice constant here is about 1.2 microns. This is created by a dry etching process. And here's a structure on the left-hand side that even a theorist can make. I actually made this through a national fabrication facility. It is possible to do this very easily because if you apply potassium hydroxide etching, it naturally exposes the 111 surfaces of silicon if you start with the 100 surface. So starting with an appropriate mask, which is made by electron beam lithography, it naturally forms these inverted pyramid structures that are depicted here. And this also has a very strong light trapping capability, provided that the lattice constant is chosen appropriately. So here are some actual optical measurements in comparison with theory of the first structure, the parabolic pore structure, as a function of wavelength from 300 to about 1100 nanometers. The red curve is the experimental result, showing very high absorption even in this long wavelength regime. The blue curve is the theoretical calculation showing the resonance structures associated with it. Actually, the experiment averages over a lot of these resonances because it's over a broad area. But nevertheless, there's very good agreement. Here we observe and calculate maximum achievable photocurrent density of just under 40 milliamps per square centimeter. This is another interesting measurement that was made as a function of angle for 4 different samples. The first, the green curve, was for a planar 10 micron thick silicon structure that absorbs only about 40% of the incident light. If you go to a planar 500 micron structure without any anti-reflection coating, I presume, then the absorption goes up. But if you put in a structure like this on the top, the bottom of these 2 red curves is the 10 micron thick photonic crystal structure, and that's not that much below the same photonic crystal architecture implanted on a 500 micron thick structures. You can see that this light trapping is really quite an effective way of reducing the thickness required for absorbing a lot of sunlight. Here is a little bit more detail of the optical absorption spectrum that we calculated, not only for the exact parabolic pore structure that Professor Lin's group created, but we also showed that if you were to put a tilt in the orientation of these pores, instead of the red curve, which corresponds to the vertical pore, the absorption could be increased even further. And here's a picture, a snapshot of the electromagnetic field profile. The yellow arrows, which you can barely see, are the pointing vector, and the colors represent the intensity, red being the highest and blue being the lowest. This is a particular resonance at 940 nanometers, and you can see this type of parallel to interface flow of the pointing vector. There's some vorticity in the pointing vector as well, creating this long dwell time in the structure. This is the outline of the parabolic pore seen here. And in this tilted pore structure, this is more evident than in the vertical pore structure. So the physics that we're talking about seems to be evident in these actual experimental structures. What I'll focus on for the rest of my talk today is going to be on these inverted pyramid structures. And as I mentioned before, the lattice constant of the inverted pyramid is what the 1 degree of freedom that you have here. After that, you just form pyramids that etch and expose the faces of the 111 surface of silicon. Inverted pyramids have been considered quite a long time in photovoltaics, going back to early work of famous scientist Martin Green back in the late 90s. He, again, was thinking in terms of ray optics, so he considered a lattice constant which is close to 10 microns, which is much longer than the wavelength of visible or near-infrared light. And this led to a world record efficiency of about 25.1% back in 1999. So you can see that the efficiency hasn't gone up a lot since that time, and the thickness of the structure that he used was about 450 microns of silicon. Now here you see some simulations for much thinner structures where the height, the thickness of the structure is considered to be 3 microns, 5, or 10 microns. And what we look at is what is the maximum achievable photocurrent density as a function of wavelength, and there's typically some optimum depending on the thickness. For the 10 micron case, the optimum is a lattice constant, this parameter A, of about 2.5 microns. And what we were able to show is that there's considerable wave interference that takes place in this structure. And for a 10 micron thick structure with 2.5 micron lattice constant, if we also put in a thin layer of anti-reflection coating on the surface to prevent some of the very short wavelengths of light from being reflected, we could bring the maximum achievable photocurrent density up to 42.5. And that's actually very close to the maximum possible, which is 43.5, which would correspond to 100% absorption of sunlight in the 300 to 1100 nanometer range. So here's some more detail of the wave interference-based absorption spectrum for different thicknesses, ranging from the red curve, which is a 3 micron thickness structure, up to the black curve, which is 10 microns thick. So each of these peaks represents some optical resonance that's being created by wave interference effects. And here, this includes an anti-reflection coating. If we don't put in a thin anti-reflection coating, we would lose about typically 2 to 3 milliamps per square centimeter. So this is the MAPD as a function of the thickness of the structure, either with or without the anti-reflection coating. And that's something that we published quite recently. In addition, we discovered that in the 11 to 1200 nanometer range, which is very close to the indirect band edge of silicon, the light trapping effects are so effective that even there's a significant amount of sunlight that's being absorbed. So this is the absorption coefficient from 1100 to 1200 nanometers in the region which would almost require phonon-assisted absorption, even into what's called the Urbach optical absorption edge of crystalline silicon. And that as well can contribute to the overall efficiency of a solar cell with this type of light trapping mechanism. So here again you see even more pronounced optical resonances associated with the electromagnetic Poynting vector and the field intensity. I think you can just barely see the outline of the inverted pyramid here. This is for a resonance at 1008 nanometers, and this is at 1040 nanometers for different thicknesses. You can see a lot of vorticity also. That's again part of the slow light mode that is being created inside the structure. And then we can integrate over all the different wavelengths to calculate the total generation rate of electron-hole pairs in this structure. So this is the inverted pyramid, and the overall height of the structure is 10 microns. And this is on an exponential scale, so red regions correspond to 10 to the 21.8 carriers per cubic centimeter, and to the blue regions a little under 10 to the power of 20. And this is what then goes into further calculation of the electronics, how the carriers that are generated then reach their respective contacts to generate power in the structure. So again, what we're trying to do is to see how much of this 33%, the limit defined by Shockley and Queisser, we can get in terms of efficiency. We can absorb not all the light, but we're getting close to that point. And then the next question is, what is the nature of the losses, the recombination rate of the carriers as they try to diffuse from where they're generated to where they need to end up at the contacts. So this involves then solving what are called the semiconductor drift diffusion equations, which are a nonlinear set of equations. G is the generation rate, which we obtain by solving Maxwell's equations, and R is the recombination as a function of position throughout the structure. And P and N correspond to the density of holes and electrons, etc. Psi is the electrostatic potential. And so this couple set of equations, Maxwell's equations and the drift diffusion equations, need to be solved to obtain the actual efficiency of the solar cell. And another important effect is what happens at the surface of a structure like this. That's where a lot of recombination occurs, and that appears as a boundary condition in these drift diffusion equations.
I have a question here. In this equation, where's the defect? You have a donor, you have an acceptor. Do you have a defect?
Well, this is on a slightly larger scale than on the scale of individual defects. So this is the density of donors, this is the density of acceptors, and this has a spatial profile that goes into it.
Deep levels?
Deep levels, okay, that is defined in terms of this recombination parameter. There's something called the Shockley-Reed-Hall model for deep level defects, and that defines a carrier recombination lifetime that goes into this parameter. So that all enters into this parameter R, which can be a complicated function of carrier densities, etc.
This is just R.
Yeah, that is what is typically done in photovoltaics, and they've done a lot of comparison with experimentally tested solar cells by using these recombination models, and I'll talk about.
You see there's one issue. When you make this inverted pyramid,
Yes.
and you're going to create a defect, I don't know what kind of defect, near the surface or at the surface.
Yes.
And that's going to change your R. So your R actually have spatial dependence, right? And
Yes.
you cannot use the same R throughout.
For the surface, as I mentioned, it is treated as a boundary condition. It's referred to as a surface recombination velocity. If that velocity is very high, that means there are a lot of defects. Yeah. But we'll try to make some contact with actual experimental studies of the surfaces and the ways in which those have been passivated to put in the right numbers into these boundary conditions as well as the bulk recombination.
Maybe we can pursue this more in the question session.
Sure. Okay, so these are the type of recombination effects, as was already pointed out. You can have deep level defects that cause non-radiative recombination. This goes under the heading of Shockley-Reed-Hall lifetime. Another one which cannot be controlled, as you can improve the quality of the silicon, you can hydrogenate it to reduce this to some extent. A very significant one is what is called Auger recombination, where an electron-hole pair recombined, rather than emitting light, which would be rather difficult in this case due to the indirect band gap, it actually excites another electron higher up in the conduction band, and then that thermally relaxes, so the energy is just dissipated in terms of heat. And at the Fraunhofer Institute in Germany, which is sort of the European equivalent of NREL, they defined a model for these recombination processes where they mainly consider, in this case, just the Auger recombination. So assuming that there is no defect-based recombination, and initially not even considering surface recombination, they considered the balance between absorbing as much light as possible and then not losing that electron-hole pair to recombinative effects. And they asked, what is the optimum thickness of a silicon solar cell? If you make it thicker, you absorb more light, but then you also have more recombination taking place. And they suggested, within a very simple but widely quoted model, that the optimum thickness of a silicon solar cell, based on these considerations, would be about 110 microns in thickness. And they also declared that based on the Auger limit, as it's called, you can't avoid this type of recombination, that no solar cell, silicon solar cell, could exceed an efficiency of 29.4%. That's already less than the Shockley-Queisser limit. But what they assumed is that the maximum amount of light that you could absorb is defined by the Lambertian limit. And what we'll be showing is that with wave interference-based light trapping, you can exceed the Lambertian limit. And in fact, the optimum thickness is much less than 110. It's probably closer to 10 microns with an efficiency that exceeds this Auger limit, which was based on the Lambertian limit. So that's what I'll be trying to discuss with you. The surface of silicon is a very important issue to deal with defects that can cause non-radiative recombination. Of course, if you have a surface, you're cutting bonds and there are dangling bonds there. You can try to remove some of those dangling bonds by various procedures. This is one that was used by my colleague in the ECE department at the University of Toronto by depositing thin layers, nanometer scale layers of hydrogenated amorphous silicon as well as doped hydrogenated amorphous silicon to try and cap these dangling bond defects as much as possible. The doping region also creates a strong electric field near the surface that would deflect the minority carriers, which also have to get to the surface for non-radiative recombination to take place. And they were able to demonstrate what is called the surface recombination velocity, which is the recombination rate per unit area, per unit of carrier density, as low as about 10 centimeters per second. So this is sort of the state of the art, and that occurs for the regions near the contacts, which is where a lot of the recombination takes place. So this is one of the sort of the state-of-the-art achievements, I think, in terms of passivating the contact regions, and those are some of the numbers that I'll be making use of in our model describing the drift, diffusion, and recombination effects. So here's an actual design of a inverted pyramid photonic crystal solar cell. We have the pyramids at the top covered by a dual layer anti-reflection coating, and then there's a region with high N doping. So the N doping profile goes up to about 2 times 10 to the 18 per cubic centimeter here. There's a very low doping region, which is P-type, which is about 10 to the 15 per cubic centimeter. We want as much low doping as possible because that reduces the Auger bulk recombination. Then finally, near the bottom, we have a high P-dope region, again separated from the contact with some passivation layer, and the contact comes up and touches the silicon in specified regions. And there's, in this case, we also consider top contacts with some dielectric surrounding it to try and cloak as much of the contact to prevent shadowing loss due to their presence. And in this case, for an MAPD of 42.5 and a surface recombination velocity on the order of 10, this 10 micron cell, assuming absorption only from the 300 to 1100 nanometer range, had an efficiency, computed efficiency at 25 degrees centigrade of 29.73%. Now we can also consider the region between 1100 and 1200 nanometers. Usually in ordinary solar cells that doesn't really do you much good because it just doesn't absorb much light at all. There's not enough light trapping, and what happens is that there's an effect called band gap narrowing. As a lot of carriers are generated, it actually lowers the band gap of silicon a little bit, and that actually reduces the voltage generated without increasing the photocurrent density. So here's some comparisons of these hypothetical Lambertian cells with 110 microns with and without this band gap narrowing. The photocurrent density doesn't improve at all, but the voltage goes down a little bit, and so the efficiency drops slightly below the original efficiency of 29.5%. If we do this for our inverted pyramid cell, we gain another milliamp or so from this very long wavelength regime. The voltage does go down a little bit, but it turns out that that actually improves the efficiency a little bit. In this case, with this top contact cell, it showed an efficiency theoretically of slightly over 30% using the recombination models that are provided by the Fraunhofer Institute to us based on experimental data. Another design, which is the type of architecture used in the current world record cell by Kanika, is to not have any contacts at the top at all, but to have all the contacts on the bottom in an interdigitated fashion, so they're alternating N and P type contacts. So there's no shadowing loss at all, and you can optimize the width of the P and the N contacts to minimize the recombination loss here. So here's a side view of the same structure, P plus region at the top and one of the bottom contacts, and a high doping N region near the other contact. And this is the generation of carriers depicted here. This is on a much larger scale. This is about 40 microns and 10 microns here, whereas the lattice constant here is about, again, 2.5 microns. And as it turns out, this has an improved efficiency relative to the front contact cell that I discussed with you earlier. So what would the Lambertian cell do in this context of an interdigitated back contact geometry? So this depicts the efficiency of the cell as a function of the thickness, H or L as I'm calling it here. And so initially, if the cell is too thin, not enough light is being absorbed, but if you go to very large thicknesses, there's too much recombination, and the optimum here, including losses at the surface and this Shockley-Reed-Hall lifetime, the state of the art for that is a 10 millisecond lifetime. The optimum thickness would be about 90 microns. And for cells that absorb less light than the Lambertian limit, the optimum thickness might be much more, and that's why the Kanika cell, which set the world record, is at 165 microns. But in the case of photonic crystals, the optimum can be much less than that. And so here again are some calculations of different inverted pyramid structures of different thicknesses going from 3 microns up to 15 microns. And there's a lattice constant which optimizes the photocurrent density. And now we're talking about absorption over the entire 300 to 1200 nanometer range. And here it turns out that actually a 15 micron cell has the best result. This is showing the photocurrent obtained by Lambertian light trapping over the 3 to 1200 nanometer range. And in the inverted pyramid cell, you gain close to another milliamp in this 11 to 1200 nanometer range. So when we add the two together and look at 3 to 1200 nanometers, in some cases we're close to 3.5 to 4 milliamps above the Lambertian limit. And that is what really allows us to reduce the bulk Auger recombination losses and go to a much thinner cell. So here again you see some of the optical spectra. This is for a 5 micron thick cell. You see a lot of resonances and wave interference effects going all the way up to 1200 nanometers. This is the 15 micron cell. This takes an enormous amount of computational time to simulate a large structure like this. But you see that it's well above the Lambertian limit, which is shown in the red curve here. And of course, the Lambertian limit ignores any specular reflections, so that is always ahead of us in the shortest wavelength limit. So it's these sort of structures that we can now consider in terms of the semiconductor drift diffusion equations. And here I plot an interesting result here as a function of the cell thickness, assuming an optimized inverted pyramid architecture on the top and back contacts only, what the efficiency would be as a function of that thickness. And we do it for several different cases, ranging from the black curve, which we assume a Shockley-Reed-Hall lifetime of, I think, 0.1 milliseconds. So that means there are a lot of defects in the structure, and there's recombination taking place at defects, up to the state-of-the-art value of 10 milliseconds, which is the blue curve. And here is where we find the optimum that a 15 micron cell would actually achieve an efficiency of about 31%. And so this is what we think combining state-of-the-art surface and contact passivation, state-of-the-art bulk passivation and reduction of defects, creating this 10 millisecond carrier lifetime, is possible with a very thin and flexible 15 micron thick silicon structure. Now I'll add one caveat to that surface passivation really is very important. If you were to make the surface recombination velocity much greater than 100 centimeters per second, you can see that the efficiency would drop rather rapidly. And there are two cases that I plot here. One in which we have the optimum doping profile, which is this red curve. So you create a back surface field to deflect minority carriers, and if you don't do that optimally and go to a smaller doping profile, it becomes even more sensitive to this surface recombination velocity. So some amateur making a solar cell that hasn't passivated the surface very well could easily take our optimum inverted pyramid cell, which absorbs so much light, but still end up with a 5 or 10% efficiency. So the surface plays an enormously important role in achieving a very high efficiency here. Okay, so where does this all stand relative to world record solar cells? Of course, if you go to multi-junction cells, the highest efficiency is up to 46%. That involves about 4 different materials stacked on top of each other, and that is with a solar concentrator that creates 1,000 times the natural solar intensity to reach those sort of efficiencies. But the more important curves are the ones down here that consist of a single material. This is thick crystalline silicon, monocrystalline silicon, and then thick polycrystalline silicon. You can see that as over many years, the efficiency has increased only slightly, but not by a dramatic amount. And then there are these other materials that are competing with that for the thin film space, the SIGs, cadmium telluride, and the perovskites that are very close to the thick polysilicon case. What we're suggesting is that with thin film crystalline silicon architectured in the form of a suitable optimized photonic crystal, these inverted pyramid structures, we should be able to achieve at least a theoretical efficiency of 31%, which would be higher even than the best gallium arsenide solar cell that has been made, and very close to that of some of these multi-junction cells. The next curve above it is a 3,5 material on top of silicon, which has shown 33% efficiency. And here's how the thickness of silicon solar cells has changed over the decades, starting from over 400 microns And as light trapping has been introduced, they brought it down to maybe close to 200 microns, but that is more statistical ray trapping. With wave interference-based light trapping, we should be able to achieve even higher efficiencies by going to the thin film regime, which is quite unexpected, actually. So in summary, let me just say that photonic crystal light trapping should enable very high solar absorption in thin films, allowing a major reduction in bulk recombination losses, which is the major barrier between the current world record and the Shockley-Queisser limit. The underlying physics is wave interference rather than ray optics, leading to these parallel to interface refraction effects, the high electromagnetic density of states that supports these slow group velocity modes and other optical resonances. And from this combined solution of Maxwell's equations together with semiconductor drift diffusion equations using state-of-the-art recombination models, we the modeling predicts 31% efficiency at one sun with up to a surface recombination velocity of about 100 centimeters per second. And one thing I didn't mention is that if you go up to a concentration of 60 suns, this efficiency actually goes up to about 34%. And finally, there's a rapid loss of efficiency if you don't have the right front and back surface fields and doping profiles and or poor surface passivation. So the challenge is to combine both the best optical structures with the state-of-the-art electronics. And finally, these structures, due to their photonic crystal architectures, have very good angular response up to about 50 degrees off normal incident sunlight, which is very valuable if you don't want to be tracking the sun throughout with your solar cell device. So let me just stop there.
Thank you for a very nice talk on the application of photonic crystals to photovoltaics.